Excellent, yeah. The slide selection doesn't work.
I mean, the slides work like this.
No, I think you need the point. That's it. We will get it.
So I said it doesn't work. Okay.
Only the laser point.
Then I'm afraid you use the this. Yeah, I'm sorry. Yeah, if you want the pointer, this does work. There's like to change. Yeah, rows before.
You see, those are the gurus of the week. But okay.
What should I introduce, or you want to introduce Blue?
Please.
Other what? Minutes.
Yeah, let's wait maybe a couple of minutes.
Then you should continue.
Okay.
Time or does it share?
Maybe that's like the pointer and the pointer.
Yes. So I will present the Miguel.
Yes.
Okay.
I don't know.
Okay.
I told you knew. No, not here.
Ah, okay. He's here tomorrow.
Yeah, not today, but no.
One minute cut off if the pointer doesn't vary.
Okay.
Okay, if it doesn't arrive in 1 minute.
Yeah.
Yeah, I'm not thinking we're not coming back now. Okay,
It was an excuse, really. How do you pronounce it? Yes, Zhejiang, no? Zhejiang University.
which one?
Zhejiang.
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 Zhejiang, yeah.
Zhejiang. Zhejiang.
Okay, this one should work.
And what
That's
do you do?
the USB just connected. Are you using this one or not?
is using this.
Yeah, so just plug it in and it would work.
I should plug it here, right?
Yeah.
Let's see.
No,
They work
no, I think no. Ah, wait. On the import.
Yes.
Okay. Okay, that's that.
So
Okay, thanks for coming. I will pretend to be Miguel today because Miguel couldn't be here. So this is a short seminar between Complutense and IFT, and today we have Wang. He's finishing his PhD in Zhejiang University, and he will talk about Kaluza-Klein AdS Amplitudes, in particular Virasoro-Shapiro and Veneziano. Please, Bo, take it away.
Thanks for a nice introduction. I'm very happy to have a chance to give a short seminar here. Today, I will talk about Kaluza-Klein AdS Virasoro-Shapiro Amplitude and Veneziano Amplitude. This is based on our recent work with AdS and by myself. I will also come on some recent work in progress. So let me start from the introduction. Okay, as we know, flat-based Virasoro-Shapiro amplitude provide a way to do a UV completion. For example, if we consider type 2V string in superstring in flat space, we know the Virasoro-Shapiro amplitude give a low energy expansion. Can I use something to pull
The pointer?
Yeah, the pointer. Okay,
Yeah.
great. This is supergraphic confusion, and this is contact terms. And if you know the contact terms, it provides some information of the R4 and D4 R4 and higher string interaction. So in a low energy, we know Virasoro-Shapiro not only reproduce the supergraphic confusion, it also provides the contact information. So from the worksheet perspective, we only have only one free parameters here, but you can see if you have any information from here, just one information to fix this coefficient, it will provide infinite power of Wilson coefficient.
Sorry, just stupid question to make sure. Why do you call this Virasoro-Shapiro? Is it scattering of 4 gravitons?
Okay. Here, I just write down tachyon, 4 tachyon, but the kinetic term is just another part, and the dynamic is controlled by this entity.
And STU, I understand.
STU is man-stem in flat space. So today I will talk about some scalar scattering, but I think the dynamic information is encoded in this amplitude. So from the well-known dispersion relation, we can see from in a flat space, we have every massive pulse, and if you look at every resistance, it will provide some partial wave decomposition, and you can extract the coupling information for all of the massive exchange from this amplitude. So we want to do similar stuff for AdS amplitude. So can we find the AdS version of the Virasoro-Shapiro or Veneziano amplitude? First, it will tell us the existence of worldsheet correlator in curved background. We want to consider AdS radius is very large, which means we turn on the RR flux. It will also tells us the bulk physics from the low energy expansion. First, we have type 2B supergalactic, and we also plus some higher derived corrections like R4, D4, R4, and higher terms. The important point is we want to use finite parameter space, finite parameters in the worldsheet formula. And these finite parameters will control the infinite power of Wilson coefficient with curvature corrections. So in flat space, we have the Shapiro or Veneziano. Here, the string length is finite. In the AdS Virasoro-Shapiro, we have this string length, which is finite, and the radius of AdS space. So the leading term is still the flat space Virasoro-Shapiro, and we'll consider higher curvature corrections with all of the Kaluza-Klein modes. So AdS CFT correspondence give us a very nice window to test this problem. On one side, we have a CFT on the AdS boundary. In the other side, we have content gravity in AdS. A very typical example is n equals 4 super Yang mills, and it's duality the type 2B string on AdS5 cross S5. In CFT side, we have a strongly coupled correlator, and in the AdS side, we have supergravity plus stringy corrections. But until now, I don't think people already know how to establish string worldsheet theory on the AdS curve background. So we can ask this question. If you have a correlator, can we also write the stringy worldsheet in curved space? So this will give us a string description in AdS. From flat space, we already know there's a partial wave decomposition. So in CFT side, we also have this conformal partial wave decomposition of the correlator here. We need to add all of the operators and its descendants. Okay. In the AdS side, we want to establish a worldsheet description for curved space. So we need this Newton like flat space, and we need to put this worldsheet on a Riemann sphere. The integral is unknown. Okay, so our task is establish what G looks like. Okay. So I have a cartoon diagram. Here we have CFT correlator, which is leading Larsen, and in the other side, we don't know what is function on the Riemann sphere, but we need to find it. This will be a very finite object. After doing the integral, it will show. We will get the information of curve background. This leading term is flat space, and this term is first curvature correction in AdS space. This coefficient encodes infinity power of Wilson coefficient. So let's look at the spectrum of CFT. So this point is a spectrum of primaries, and there will be an infinite power of descendants. Okay, every primary we have an infinity of descendants. However, when we consider the flat space string spectrum, we know for Veneziano and Virasoro-Shapiro, there's always some integer spectrum. So how can we relate it up? Okay, that's a way to relate it up. We'll talk about this later. So today our key point is use the AdS CFT correspondence as constraints and translate this problem as a bootstrap problem. So on one side, in CFT, we have conformal blocks decomposition. In the other side, we want to establish a worldsheet formula for the curvature correction of the AdS Virasoro-Shapiro. So when we identify this object, it will give us the constraints. So after we solve these constraints, we'll automatically fix all of the first curvature correction and give a unique solution. Okay, so first we will consider simplest case, which is a straight tensor, this O2, and then we will consider generalize it to arbitrary Kaluza-Klein modes, and then we will predict OPE and unknown dimension from CFT side. Okay, we consider this worksheet. We'll find finally we need some single value functions, and this will give us will define worksheet description, and we will consider a Fourier transform to relate to the CFT spectrum and the overlap spin spectrum. So let me start from the Virasoro-Shapiro. Here we consider four straight tensor, and we have a super conformal block decomposition in mailing space. Here we have primaries and its descendants. On the numerator, we have OPE coefficient and map polynomial. So this polynomial is just similar stuff like Legendre polynomial in flat space, which is already known. We need to do the Fourier transform. It removes the divergence in AdS space and send it to flat space. Okay. So traditional, when we do the Fourier transform, we just send these correlators from CFT to a flat space. However, there are more informations. If you keep these informations, you will see more curvature corrections. Okay. So let's deal with this unknown dimension and OPE coefficient. The leading term will be controlled by flat space. So this twist 0 equals the closed string spectrum, and this OPE coefficient is fixed by flat space Virasoro-Shapiro amplitude. And we also have higher curvature corrections, which is tau 1, tau 2, F1, F2. This is unknown, but we can solve it. So how can we resum this descendants pose? We just send it to an integer, and you will see in the Fourier transform we have an exponential. After doing this integral, we will see there are some higher pose of S. Okay, in flat space you can take this I equals 2. Okay, if you take I equals 2, you will find this is just some simple pose appears. Okay, you will find some simple pose in Virasoro-Shapiro, which is the structure of flat space amplitude. However, here we have higher I, so we'll have I equals 2, 3, 4, and you will see in this CFT story we have higher order pose of S. This is from CFT. We also need to find similar structure in the worksheet, okay, to compare both sides.
So the scaling lambda to the 1/4 is
Here,
is motivated. The scaling tau with tau naught lambda to the 1/4.
this one.
Yeah.
Every stuff will be averaged.
No, I mean the scaling is motivated by integrability because one knows the spectrum at large lambda.
Yes. If you consider O2, 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 it will be the unknown dimension of Konishi and something. You can predict, and you can compare this result with integrability results. However, in our situation, because we consider lambda is very large, it's near flat space. First is flat space and then curvature correction. You will see the difference between these operators. You can see that. So it becomes some average data. So you can see this picture. There are some a lot of modes for every massive exchange. We cannot distinguish them from our computation. So all of these data will be sum over to your average data. Okay. But if you want to consider this leading trajectory, you can do that.
Yeah.
And for a sub-leading trajectory, if you already know what is the data of this stringy modes, you can do unmixing. But I don't think people know this data explicitly. So now let's write down what's the basic structure from a CFT prediction. After doing the Fourier transform and the largest expansion, we will see the final amplitude will have higher order poles. For every curvature correction k, there will be a pose like s minus delta to 3k plus 1. So you can imagine if k is 0, so it's just a simple pole, like flat space. Okay. If you consider k is 1, we have quadrat poles and sub-leading poles. You will see these descendant poles will overlap together. Okay. Become some overlapped integer poles. So now we need to find from a string theory perspective, how does this pose behave like that? Okay. Actually, it comes from well-defined worksheet integer. Let's motivate from the flat space Virasoro-Shapiro. So Wilson coefficient of Virasoro-Shapiro amplitude lying in the range of single value multiple polylog. It comes from a simple worksheet integer on the Riemann sphere. Okay, looks like this. And we can construct this single value multiple polylog as our basis. It satisfies a simple differential relation, and if we set this one is 1, you can solve this relation and fix all of the higher transcendental weights. Okay, we can put 0 and 0, 1, 0, 1, 1, something like that, and you solve this equation. This is a well-defined object, and we just need some weight 3 functions. So we will combine these functions as symmetric and anti-symmetric parts. So on the Riemann sphere, you can see what's the difference of single value polylog and not single value polylog. It looks like if you just choose log z, there's a branch, okay, on the Riemann sphere. And if you combine log z plus log z bar, you will not see the branch on the Riemann sphere. That's a total difference. Okay, we want to construct our Virasoro-Shapiro amplitude by 3 integers, which is crossing symmetric. And every integer over Riemann sphere have a very lives in a finite parameter space, and we can explore their S-channel OPE. If we set z to be 0, we will find some log divergence. And after integrate this log divergence, you will also see the higher order poles. So we will generate this pose from worksheet integer like this. So now we have both sides. One side we have pose from CFT. On the other side, we have pose from worksheet. If we can compare both sides, and this will give us the constraints, and we can solve these constraints and obtain the final result. Okay, let's just talk more about basic structures. We can also expand the curvature corrections, and k equals 0 is flat base, and k equals 1 is what we want to deal with. For general k, the structure is clear. We have some homogeneous numerator, and u squared is universal. And we also need ask what's the function basis of this integrand. we will say here, this is a single value functions of transcendental weight 3k. So when k equals 1, we will use some pure weight 3 function. So what you need to do is matching the block decomposition with S-channel OPE from worksheet and the conform block decomposition. The number of single value bases with fixed weight and singularity is finite. However, the low energy expansion of this integral includes infinity Wilson coefficient. So we can solve this worksheet integral and fix all of the free parameters. And apply this to O2, 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 and O2, O2, OP, OP will give us, okay. So for O2, 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 we can evaluate this to second curvature correction. For O2, O2, OP, OP, we can solve it to first curvature correction. And we can look at the low energy expansion of mailing amplitude. It will organize the low energy expansion like first, the leading term is fixed by the flat space Virasoro-Shapiro, okay, which is totally null, and the subleading is unknown. However, after fix the A1, we can recover this unknown coefficient in a low energy expansion. Okay. Okay. Now the challenge is how to consider the Kaluza-Klein correction. If you want to use dispersive sum rule, it will tell you deal with the super conformal block decomposition of general Kaluza-Klein modes is very hard. The SU4 symmetry is very complicated, and you need to do a lot of computations. So it's not very convenient just to consider a specific Kaluza-Klein configuration. How to avoid the challenges and derive a uniform formula for arbitrary KK modes. The key point is introduce a discrete mailing transformation on the sphere S5. So after introduce this discrete mailing transform on S5, we'll see the distance on sphere S5 behavior like this. If you don't do this transform, there will be a lot of gamma functions, and there will be a lot of power of the distance. However, after doing this discrete mailing transform, you'll find in the final result, the discrete mailing variables Nij is linear or quadratic on sphere. So this is introduced in. There are several papers deal with some supergravity string corrections and some higher point scattering. You'll see after introduce the discrete mailing transform on S5, the final result can be very simple. Okay, it's also simplified the tree-level scattering for supergluons and the supergravities. Okay, if we write down the Fourier transform and the discrete mailing transform simultaneously, we will find for mailing transform, some people doing the discrete mailing transform and from here to here. This is discrete mailing variables on the sphere. It will generalize all of the Kaluza-Klein modes in the distance space. And we can also use Fourier transform for a specific Kaluza-Klein configurations from a mailing amplitude to a Virasoro-Shapiro amplitude in AdS space. However, no one consider, can we introduce the discrete mailing transform for the Virasoro-Shapiro amplitude to write down a generating function to generate all of the Kaluza-Klein saturations. So this is what we did. Just consider the discrete mailing transform for the Virasoro-Shapiro amplitude in AdS space. This will become a generating function and generate all of the Kaluza-Klein scattering in AdS space. So what we need to write down is MCAS, which is depend on the discrete mailing variables on sphere. So for convenience, we can construct NS, NT, and NU, and you will see the crossing symmetry on these variables is very simple. Okay, so we can combine this representation with worksheet. What we need to do is not very hard. We still need some homogeneous rational functions in ST and U. However, we will change their coefficients. Okay, we need to add some dependence of sphere variables of this F1, F2, and F3, and still have a U square. So Fij is combination of NS, NT, and NU with unknown coefficient. We need impose crossing symmetry. It tells us the amplitude is invariant under the exchange of Z and 1 minus Z, and NS change with NT. The single valueness is automatic because we use single value multiple point logs. So the final results still rely on the single value multiple zeta values. And we will matching the knowing results O2, O2, OP, OP, which is already done for AdS Virasoro-Shapiro amplitude. And finally, our result will recover the supergravity contributions. So let me write down the final results. It's not very hard because we just introduced the new dependence of these sphere variables. The final result depend on 5 linear multiple point logs, and you can find it in our paper. And the coefficient is just linear. Okay. Next, I will.
So just one question. So you used the result for 22pp
Yes.
as a. You could not do it without 22pp, or you could.
I can. So here, in this paper, the point is we can consider discrete mailing transform on sphere S5. So if you already know what is Virasoro-Shapiro, AdS Virasoro-Shapiro with some specific Kaluza-Klein modes, you can uplift them to this discrete mailing space. It depends how many information do you have. Right. If you write down a project or project dependence of Nij, you cannot fix them using O2, OP, OP.
Right.
Because if you write 1 or NS in this space, and you can fix them using O2, O2, because the unknown parameter is 1 or 2. You just use one condition to fix the coefficient. And if you want more dependence, like linear dependence, like 1, NS, NT, and NU,
Yes.
you need more information because this transform looks like send this finite space to some another space. It still have keep the dependence of free parameters. The question is, can you fix these parameters with some KK dependence? So O2, OP is enough to fix the linear dependence. So that's a point. So what we did in this paper is just we said we can construct the ansatz in discrete mailing space and then fix this all of the free parameters in this space using knowing results. That's the point. However, we find there's a general picture of Kaluza-Klein stringing amplitude. We don't need to consider a specific Kaluza-Klein situations. So what you ask is here, this is necessary or not? Actually, it's not necessary. So in our paper, we said, okay, we can, if you know this, we can construct ansatz and fix all of the ansatz here. And in AdS3 cross S3, you can also do that. First, work out O2, O2, OP, OP. This is a specific Kaluza-Klein configurations. However, I find it is not necessary to work in a specific Kaluza-Klein configurations. We can relate the mailing amplitude, which is the CFT description, directly to a worldsheet description. And both of these objects lives in the discrete mailing space. Okay, then we need to consider the Fourier transform between these two objects. You will find the constraint is enough to fix this Virasoro-Shapiro amplitude, Veneziano amplitude, in general holographic background. So this is my recent work, and it on archive. So now we work in this discrete mailing space. First, we still consider superblock decomposition, which is described by a reduced correlator, and this is OPE, which is no, and the control block, still no. For the subleading term of this OP coefficient, we don't know anything about it, but we can solve it. In mailing space, we still write down this block decomposition, and doing the Fourier transform, send the spectrum from CFT to a flat space. This pose will overlap with each other, and you will see after doing this, let's say, Fourier transform and the lattice expansion, the map polynomial will decompose in Geigenball and its derivatives. So we have after doing the X integral, which is come from the sum of descendants poles, you will see there's a lot of higher order poles, and the numerator is you can fix them. So how do you fix them? The map polynomial, we know that the explicit expression, and this f, we just expand them into in a large twist. So we'll have some average the OP data. I write this polynomials explicitly. So f0, all of the f0 is fixed by the flat space, Veneziano amplitude, and this twist2 is unknown. Okay, f2 is still unknown. However, we also write down a worldsheet ansatz, which is finite, and there are just several free parameters in this expression, and we explore the S channel OP, send z equal to 0, and still we have some log divergence. After doing this one-dimensional integral, you will see there are some higher order poles. But the point is, this is a finite. The function space is finite, so parameter is finite. However, in a CFT side, there's infinity coefficient here, because you can choose theta equals 1, 2, 3, 4 to infinity. There's infinity functions you can match. Okay. After doing matching the quadratic and 4 of these poles, you will find all of these unknown coefficients will be fixed. And worksheet ansatz is also fixed. So matching the knowing F0 data, complete fixing the ansatz, which further determine all of the unknown coefficients appear in our ansatz and the block decomposition.
So this method is just compatibility with two different representations.
Yes. So the point is here, if we write down a CFT decomposition and in other side write down worksheet ansatz, and after you identify these two different objects, it will provide you an infinity constraints. And after fixing part of that, you'll find all of the equations is satisfied and all of the parameter is fixed. So this is a general picture. I believe for the general holographic model, you can check. So in this paper, I use open string scattering for Veneziano. And I also checked in AdS5 cross S5 for the Virasoro-Shapiro amplitude. It also satisfies these constraints. And for AdS3 cross S3, they did 2-2pp. So I believe for the general Kaluza-Klein mode, you can think about this is right. And there's still some another holographic model like AdS4 cross S7 mode D2, something like that. Here they just do some specific. I think it's O2, 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 O2 in that paper. So no one did higher Kaluza-Klein modes. So this is still unknown, but it's interesting to check.
But just to summarize, you can fix everything in the case in which the single values are weight 3.
Okay, so I should say for the Veneziano amplitude,
Right.
this is weight 3 and lower weights.
Yes, I see.
In AdS5 cross S5 and AdS3 cross S3, they are pure weight 3. But I'm not sure this pure weight 3 come from the.
I mean just maximum weight 3. You don't go.
I'm not sure. So maybe you will solve. This is because the maximal supersymmetry. But actually, in AdS3 cross S3, this is not a maximal supersymmetric object. So maybe this is related to the closed string and the open string.
I think weight 3 because the logs that you get when you do the Borel transform, it gives you some right power of the poles in S.
Yes.
But if you consider weight 4 and
yes.
higher weight, do you think that the compatibility between the two representation is?
You can do it to second curvature correction. You will have higher order poles. Here. No, here. You can see if you consider higher curvature correction like k equals 2, you will have weight 6. So it's still pure weight. But after you consider the S channel OPE, after you consider the S channel OPE, you will have log and the highest weight is still maybe for second curvature it's weight 6, right? Sorry, but you still have some log 1 minus z.
Okay.
If you expand log 1 minus z, you will not obtain log z. So you will have some weight 5, weight 4 terms, and this will gives you some lower order rows. So I just say the function basis is pure weight. I'm not sure this is related to the maximal supersymmetry or because we consider the closed string scattering. This is not sure. So maybe we need to check more modes, more holographic model, and get the answer. So questions. Our work established a universal framework for computation curvature corrections to AdS Virasoro-Shapiro and Veneziano Amplitudes with arbitrary Kaluza-Klein modes. Our worksheet ends up easily constrained CFD data by massive stringy operators at lower order and predict the higher order corrections. It's also interesting to generalize our method to higher order corrections like second order corrections. This is in progress, as well as other background like AdS3 cross S3, like AdS4 cross CP3, and something else. We can also consider the reg behavior and other special limit. This will related to another interesting physical progress, like iconal scattering or something. And finally, it's also important to consider the KLT relation and monodromy relation because we already know in flat space, after working out the KLT relation, we know we have BCG relation, and we also have CHY formula from the string scattering perspective, and this will tell us a lot about gauge duality, gauge gravity duality, and something else. Okay. So, okay, I think I still have some 7 minutes, but if you have any questions, just discuss.
Thank you. If you have questions, please go ahead. We'll write in the chat.
So the remaining two directions in the so this is the F theory background, right? The AdS5 cross S3. This is an
AdS5 cross S5 for the closed string, and you can also consider AdS5 cross S3.
So this is Haroni, Fayetudin,
Yeah.
So, but remind me how. I mean, there must be two more directions, right?
Two more directions.
They're still in to be. And theory is still to be. It's a different language for to be. So what is missing? And then two probably.
Can you repeat the?
A theory doesn't live in 8 dimensions.
Doesn't live 8 dimensions?
No.
No. First, for the AdS Virasoro-Shapiro is on 10-dimensional, right? This is a closed string scattering. So you are asking what is open string scattering?
So you wrote there AdS5 cross S3.
Yes.
That is the total of 8 dimensions. What are the remaining 2?
So we consider gluon scattering. They live on the AdS.
You mean that you only care about what happens on the D7?
Yeah.
What you mean?
Yeah.
This is the reason that you don't care.
If you
You also wrote AdS3 cross S3.
Yes, that's another background.
But what is that? AdS3 cross S3 cross T4?
There are some we can consider 0, but not we. They consider the 0 citation on another, maybe K4, maybe K3 or T4. Right. That's they didn't consider citation.
It doesn't matter what the difference between the two doesn't.
Yes, there's no difference between these two backgrounds because they consider 0 mode.
Yeah, they don't consider excitations around those directions.
Yeah.
Okay.
So it just the AdS3 cross S3 matters.
So in this work, basically, you always focus on the AdS cross sphere, and if there is something else, you ignore it.
Okay, I know another background is AdS3 cos S3 cos S3 cos S1. That's also something people know. But the problem is we don't know how to deal with this background using the CFT method. This is still unknown.
You mean the CFT dual?
Yes.
No.
Yes. Not unknown. We don't know how to use it very fast also. For this
There are
background,
proposals. There was a recent paper by Witten.
okay.
Might be interesting.
Okay. For this background, we know how to deal with the CFT dual very fast
Yeah,
and
yeah.
very quickly. So we can relate it both sides very quickly. So you can, if you know how to do this relation, you can do some work in other background.
So, but basically, whenever you have products of highly symmetric, maximally symmetric spaces, then you can proceed.
If you have half maximal, it also work. Oh, Wang is half maximal.
Okay.
If you doesn't have super symmetric, if you doesn't have super symmetric, I would say the function basis is unknown. You might imagine there are some worksheet object, but we don't know how to write down the function space. That's the problem. If you know function space, if you are clever enough to find the function space, you can also do bootstrap. On one side, you have CFT. On the other side, you have worksheet of some functions, and you identify these two objects. I will tell you, this is infinity. There are infinity functions you can solve. So this will tells you what is function base, what is the unknown coefficient of these functions. So the problem is for less supersymmetry, we don't know what its function basis are.
But just a clarification, when you do AdS3 times S3, it's doing just 3 levels, so it doesn't matter the other manifold, whether it's T4 or K3. But then it depends, when you go one loop, it depends which manifold. So one loop will know which manifold, which theory is studying. Just that it's a coincidence. If you do 3 levels, it doesn't matter. And similarly for the AdS5 times S3, there is another sector, which is the sector covered to the graviton, and that is way harder than just looking at the theory and the word volume of the set.
But what if you add some citation in tree level? So the mode is different.
I mean, because the tree level for the gluon, it would be like 1 over n, and then the first coupling with the graviton is 1 over n squared. So it would be one loop of gluons will mix with tree level when you couple also the gravitons.
Yes.
And then everything is mixed. But if you just look at tree level, then there is some special situations. So are there more questions for Bo? There are no questions from the chat. I will count to 3, 2, 1. Solved it. Okay. Let's thank you for again. Minutes.